Hello students, we are going to start a new chapter today. It is torsion. Shaft is an example of a member in torsion. Shaft is used in many applications in engineering field. It is used to transmit power from motor to the machine tool, from engine to the rear axle, from turbine to the generator. You must have seen the shaft being used in many applications around yourself. Now these shafts can be either solid or they can be hollow also. Now due to twisting movement on shaft, shear stresses develops in them, and these shear stresses are set up perpendicular to the radius at all the transverse section. As a result, there is going to be complementary shear stress which will develop on the surface of the shaft or the longitudinal plane, which causes the distortion of the filament on the surface. In a moment we are going to see this thing in detail. Before going further and deriving the relation for the torsion of the shaft, let's look at the assumptions which are involved in this derivation. The first assumption is that the material of the shaft is homogeneous, it is isotropic and perfectly elastic. It obeys the Hooke's law. That means we haven't stressed the material beyond the elastic limit. So stress remains proportional to strain. Okay. So here we are talking about the shear stress. So the shear stress tau remains proportional to shear strain phi. So we are talking about that, which means that it obeys the Hooke's law. The twisting couple acts in the transverse plane only. So we are applying the couple or the moment or the torsional moment, and it is acting in the transverse plane. All radii remain straight after the torsion. So if you take any cross section of the shaft, which is a circular shaft, and you take any cross section, you draw the radii on that cross section before applying the torsion and after applying the torsion, you will find that those radii will remain straight, they will not get distorted. The parallel planes normal to the axis do not warp or distort after the torsion. So that means if you take any plane, any cross section, if it is circular, it is going to remain circular after the deformation. It is not going to become ellipse or something else. And the cross section at any axial length rotates as a rigid plane. Okay, so these are some assumptions. Apart from that, we have assumption that the torsion is uniform along the rod, and all normal section at the same axial distance suffers equal rotations. So these are some assumptions that we discussed now, and now let's talk about the torsional relation. So what you see here is a shaft. This is the cross section of the shaft. Okay, and we have taken a surface which is at a distance small r from the center. So we are talking about this surface, and this surface is shown here in this figure, also in another view. The length of the shaft is L, and we are taking a surface of the shaft at a small radius r from the center. Okay, the shaft is bigger here, so the total radius of the shaft may be capital R. Okay, so we are taking a surface which is inside the shaft, okay, which is at the radius small r from the center. So this is the figure for that. For the moment, please focus on this figure. We are applying torsion torque T here. This is the center of the shaft is O. A radii is shown here by OA, and because of the application of torque, the OA shifts to OA dash. That means it takes angular deformation theta here. So as we have assumed that the shaft is fixed at this end and it is free at the other end, and at the free end we are applying the torque T. So the cross section is rotated through angle theta, shifting the radial line OA to OA dash. So because of this shift in the radial line, this will cause also the filament, I can say, let's say this is C point here. So from CA it gets rotated to the CA dash by an angle phi. Okay, so on the radial part the deformation is from OA to OA dash by angular deformation theta, and on the surface part the filament CA get moved to the CA dash. There is a shear strain of phi magnitude that is there. So let's say that tau is the shear stress intensity at the surface of the shaft at this point. So shear strain phi can be written as tau by G, okay, because we know that stress is proportional to strain, tau is proportional to phi, and we replace it by tau equal to G times of phi. You must have remembered the G is here, the modulus of rigidity, so you can write that for phi is equal to tau by G, where phi is the shear strain, tau is the shear stress, and G is the modulus of rigidity. Now from this figure also, because we know that arc AA dash can be written as R times of theta, at the same times it can be written as L times of phi. So that's why phi times of L will be equal to R times of theta, which is equal to arc AA dash. We will use this relation to find the value of phi in terms of theta and L as R theta by L. Now this is equal to tau by G from this equation. So this gives me tau by R equal to G theta by L. So this is an important relation here between shear stress, angular deformation theta, and the fiber we are talking about situated at a distance R. This also tells us that the intensity of shear stress is proportional to the distance of the point from the center, okay, because tau is proportional to R. You can see from this relation first that tau is proportional to R. R is the distance of that fiber we are trying to find the stress value. So its distance from the R is distance from the center is R, so the tau is proportional to R. So this is the relation that we get here. Now let's try to work out the relation of the other part, which is related to the resisting torque. So T is applied torque, so this applied torque must be balanced by a resisting torque. So that what is that balancing torque, from where it is coming? It is coming because of the stresses that is being produced here. So the moment of the tangential shear stress on any transverse section will provide this resisting torque. So what is happening, that if you look at this cross section here, you have a shear stress value tau acting at a distance R, and we are considering a small this red element which I have shown here. So this is the red element which I have shown here. So the radius of this element is R, small r, so the circumference will be 2 pi r, and the thickness of the element is dr. So the area on which this stress is acting is 2 pi r multiplied by dr. So stress multiplied by area gives us the force. So that's why the shear stress tau multiplied by the area on which it is acting is 2 pi r multiplied by dr gives the amount of force acting on this element. And if we want to find the moment because of this force, we multiply it with the r. So that gives us the moment of the force into distance. So tau into 2 pi r into dr is the force, and that multiplied by r is going to give us the moment. So that is what is being explained here. So tangential force on the element is tau multiplied by the area on which it is acting, because I told you this is the elemental ring we are talking about here. The ring has the radius of r, it has a width of dr, so the circumference is 2 pi r multiplied by dr is the area on which the shear stress tau is acting, so that gives us the amount of force. Now moment of this force will be, if you multiply it with further by r, so that gives you the moment of the tangential force on this elemental ring. Now if you want to find the complete resisting moment for the whole shaft, which is equal to the applied torque T, so T will be equal to integral of tau times of 2 pi r dr dot r. Okay. Now if you see the equation 1, the equation 1 gives the relation between the tau and r. Tau will be equal to g theta by l into r. So we will substitute for tau here as g theta by l into r from the equation 1, and you will have the term g theta by l integral 2 pi r dot dr multiplied by r square as equal to applied torque T. Okay. Now we know that integral of 2 pi r dr dot r square, which is nothing but the elemental area delta A multiplied by r square, represents the polar moment of inertia about the longitudinal axis of the shaft, which is represented by J. Okay. So we have already talked about the moment of inertia. Moment of inertia are or second moment of area. So that is the small elemental area multiplied by the square of the distance of it from the axis. So here the axis is longitudinal axis, its distance from the area from the axis is small r, so square of it r square multiplied by the area integral is your moment of inertia or the polar moment of inertia about the longitudinal axis, which we represented by j. So if you substitute for this integral quantity as j, for this here is if you substitute j, this will give you t equal to g theta by l into j, which can be written as t by j is equal to g theta by l. So this gives us the equation second. Now if you look at the equation 1, which is g theta by l equal to tau by r, here you get g theta by l equal to t by j. If you combine all these first and second equation, you will get the relation for torsion as t by j equal to g theta by l equal to tau by r. So that is our primary or the main relation for the torsion, which relates the applied torque with the amount of shear stress that is being produced with the angular deformation that is happening in the section theta. Now this relation looks very much similar to the relation that we obtained for the bending. You must have remembered the relation for the bending stresses. It was m by I equal to E by R equal to sigma by Y. So here T by J is corresponding to m by I. You can see here by the comparing these two relations, and your g theta by L is comparable to E by R, and sigma by Y is comparable to tau by R. Okay, so sigma was stress here, bending stress, here tau is the shear stress, y is the distance of the fiber where you want to find the bending stress from the neutral axis, small r is the distance of the fiber from the center of the shaft. Okay, so these are very similar. M was the applied bending moment there, here T is the applied torque here, I was the moment of inertia about the axis, and J is here the polar moment of inertia about the center. Similar way, E by R is corresponding to your G theta by L. E was the modulus of elasticity, here G is the modulus of rigidity. R was 1 by R was curvature here you are getting the theta angular deformation, and the L the length of the shaft here instead of that. So let's define few more terms using this analogy between the bending and the torsional relation. So we define J by R as the torsional or polar section modulus. Okay, you remember what was the section modulus there? It was I by Y, which we represent by Z. So Z was equal to I by Y, moment of inertia divided by the distance of the fiber from the neutral axis Y. So that was called as section modulus. So instead of I you have here J, instead of Y which was there you have the R. So that gives you the section modulus, or where R is the radius of the shaft. Now the torsional stiffness is given by K is equal to T by theta. Okay, so this is equal to GJ by L. Okay, because what is the stiffness? If stiffness is force divided by deformation. So here instead of force you have the torque, and the deformation, instead of linear deformation you have the angular deformation theta. So because the stiffness is force divided by deformation, so the torsional stiffness can be defined as applied torque divided by the angular deformation theta. So that gives us the torsional stiffness K. Sometimes we represent it by KT also, and as T by theta will be equal to GJ by L. If you look at this relation here, so T by theta will be equal to G times of G into J by L. So you can also represent the torsional stiffness as GJ by L. What is GJ? GJ is your torsional rigidity. Modulus of rigidity multiplied by the polar moment of inertia gives you the value of torsional rigidity. There is a corresponding term in the bending where we have the term E into I. E was the modulus of elasticity, I is the moment of inertia. What was that? It was flexural rigidity, right? So EI we defined there in the bending as flexural rigidity. A comparable term here is there which is called as torsional rigidity, and its value is G into J. Now let's look at the distribution of the shear stress. As we just find out that the shear stress is proportional to the radius R, or distance from the center. So at the center, obviously when R is equal to 0, your tau is equal to 0 from your formula, and at the maximum for small r equal to capital R, or the radius of at the extreme radius of the shaft, you have tau max value, the maximum shear stress value T into R by J. In between, from center to the surface of the shaft, the stresses varies in a linear manner because tau is proportional to R. So that's why you get this straight line here from 0 to tau max. So this is the distribution of the shear stress shown along the cross section of the shaft. So you get the maximum shear stress at the surface of the shaft, zero shear stress at the center of the shaft, and varying from 0 to maximum in a linear fashion. You can calculate the value of shear stresses at the surface of the shaft, or the maximum shear stress. Like I would say, this is the tau max. So tau max can be calculated by substituting capital R equal to d by 2, where d is the diameter of the shaft. So capital R is equal to d by 2, and your polar moment of inertia we know is given by pi by 32 into d4 for a circular section. So you substitute it over here. From this you calculate the value of tau as 16 times of t divided by pi d cube, okay, where d is the diameter of the shaft, t is the applied torque. So using this relation you can find the shear stress value, or the maximum shear stress value, which is occurring at the surface of the shaft. You can do the similar thing for the hollow shaft also. So here in this figure you are shown a hollow shaft which is having inner diameter as small d and outer diameter is capital D. So if you see here, because there is no material at the center, so there we will not talk about the stress at the center because this is a hollow shaft. So you will start from the inner radius. Inner radius is small d by 2, outer radius is capital D by 2. So you can find the value of minimum stress tau min by substituting in the relation as small d by 2, and you can find the maximum stress by substituting in the same relation as R. Instead of R you substitute capital D by 2. So here I have shown the formula for calculating the maximum shear stress which is occurring at the surface of the shaft. So for R you substitute capital D by 2, the outer surface of the fiber, and what will be the value of polar moment of inertia for a hollow shaft? That is pi by 32 capital D4 minus small d4. Okay, so when you substitute it over here, you will get it as 16 times of t into d divided by pi d4 minus small d4. And the variation of the stresses are shown here from minimum to maximum. There is a linear variation here. So the stresses are minimum at the inner fiber, maximum at the outer fiber. So this particular graph show the stress distribution from inner surface to the outer surface of the shaft. Now as the shaft is used for determining the power, transmitting the power, so the power and torque relation is very important for us because we are going to use it very frequently in all the numericals. So shaft is used to transmit power. So power is given as work done per second. So if you have the power given in watt, you can represent it by T times of omega. What is omega? Omega is your angular speed in radians per second. So if you have the speed in revolutions per minute, which is n, which is represented by n, so you can write omega as 2 pi n by 60. Remind it, this omega value is in radians per second here. This is in radians per second. So if you know the value, the shaft is rotating at certain rpm, so then you need, instead of omega, you need to substitute 2 pi n by 60. So n is here in rpm. So this gives us the power P relation with the applied torque as 2 pi nt by 60, where T is given in Newton meter. Okay, if power is given in horsepower instead of watt, so you will divide it by 75 also, and you will get the relation as 2 pi nt divided by 4500 instead of the relation shown here, because we are using the SI unit. Mostly in the numericals you are given the power in watt. Now let's look at this numerical and let's try to solve this numerical using the things that we have learned. So we are given a solid shaft which is transmitting power of 100 kilowatt at 150 rpm. So in this numerical you are given the power which is being transmitted with the help of shaft, and the value of it is 100 kilowatt. That means 100 into 10 to the power 3 watt. The rpm of the shaft is given, so that means capital N value is given as 150 rpm. It is given in the numerical that the maximum torque transmitted exceeds by the 20% of this what you are going to calculate from this relation. Okay, so occasionally there may be a variation of the torque values, so the maximum torque value is 20% higher than what you are going to calculate from the numerical from the formula. So shear stress value which is not to exceed for the material is given as 60 megapascal. This is the permissible stress value for the shaft material which is being used. The shafts are usually made of ductile material, so it may be made up of, let's say, mild steel, and for mild steel the permissible shear stress value is given as 60 megapascal. In this case, you need to find the diameter of the shaft. Also, you need to find the maximum angle of twist in the 4-meter length of the shaft. So the length of the shaft is 4 meter. You need to find how much is the maximum angle of the shift twist that is happening here. You are given the value of modulus of rigidity G as 80 gigapascal for the shaft material. Now let's proceed to calculate the values here. And you see we have the value of power P equal to 100 kilowatt, N is equal to 150 rpm, length of the shaft is 4 meter, maximum shear stress that is permissible is 60 megapascal, the modulus of rigidity G is equal to 80 gigapascal, and beside this we are given that the torque exceeds 20% by the maximum value as a maximum value. So you use the relation that we have just seen here for the torque and power relation, and as P was equal to 2 pi nt by 60, you can write the value of torque as 60 P divided by 2 pi n, and that gives us the value after substituting P equal to 100 kilowatt, that is 100 10 to the power 3, for n equal to 150 rpm, that is substituted here. The torque can be calculated as 6366 Newton meter. Now because the maximum value exceeds the 20% than this, so you have to multiply this value by 1.2 in order to obtain the value of maximum torque that is being applied as 7639 Newton meters. Now the formula that we have derived between the torque and the shear stress, that was tau is equal to 16T divided by pi d cube, and you substitute the value of tau equal to 60 and torque is equal to 7639 into 10 to the power 3. You can calculate the value of D is equal to 86.8 millimeter from this relation. You see here the value of the torque was given in Newton meter, so you need to first convert it into Newton millimeter. So that's why you have the value as 7639 into 10 to the power 3. And in order to calculate the value of D from this formula, you need to take the cube root. So you must know how to use the calculator in order to find the cube root from this formula. Now the maximum angle of shift can be obtained by the other part of the relation that we have derived, that was tau by r equal to g theta by L. So for tau you substitute as 60 megapascal, so that is 60 here, because you know that megapascal is equal to Newton per millimeter square. So because that's why you have just substituted here 60. For r you have substitute d by 2, that is 86.8 divided by 2, you have just calculated the value of the diameter. For g you will substitute 80 into 10 to the power 3 Newton per millimeter square, because gigapascal is equal to 10 to the power 3 Newton per millimeter square, and you substitute theta here. Length will be 4000 millimeter, because 4 meter was the length of the shaft, and then you can calculate the value of theta as 0.06928 radians. Always remember the value of the theta or angular deformation that you will calculate from this formula will be in radians. Or if you, in case you need to substitute the value of theta which is given to you in the formula, in the numerical in degrees, you first need to convert it into radian, then only you can use it into this formula. So as you have got the value in radians from this formula, you need to calculate the value in the degrees. You need to multiply it by 180 by pi, so that you can obtain the value of theta in degrees. So that's it from the today's lecture, and in the next lecture we will do some more numericals and calculate the value of stresses, or maybe the dimensions of the shaft or the angular deformation, by using the various details which are given into the numerical.